Welcome friends, Igor is here, and in this video we will discuss matrix representations of linear transformations. In this lesson we will define matrix representations of linear transformations and compute matrix representations of two linear transformations. Let's get started. To put the new ideas we will develop today into perspective, let me first remind you what we already know about linear transformations that go from the vector space of column vectors to the vector space of column vectors. In one of the earlier videos, we have discovered that all such linear transformations are in fact multiplications by a fixed matrix. We called this matrix A a matrix representation of that linear transformation T, and we discovered how to construct this matrix. We took a basis of the domain, which consisted of standard unit vectors. Then we applied this linear transformation to each of those vectors, and we used those values, which were column vectors in the codomain, as columns in the matrix A. So we defined this matrix representation column by column, where each column is a value of the linear transformation T on one of the standard unit vectors. This procedure does not automatically extend to arbitrary vector spaces, because if the codomain is not the vector space of column vectors, then these values are not columns and we cannot use them to construct a matrix. But there is a workaround using vector representations. Let's suppose that T is a linear transformation from a vector space U to a vector space V. Let's assume that U is a vector space of dimension n and V is a vector space of dimension m. We will fix B a basis of the vector space U and C a basis of the vector space V. Then the matrix representation of the linear transformation T relative to the bases B and C is an m by n matrix, which is defined as follows. First, we compute the values of the linear transformation T on each of the vectors of the basis B, basis of the domain. These values are vectors in the vector space V, and then we will apply the vector representation function rho C to these vectors. After we apply vector representation rho C, we will get column vectors, each of which is of size m, and we will use these column vectors as columns in the matrix representation. Here is a slightly more visual definition of this matrix. Let's say that the basis C of the vector space V consists of vectors v1, v2 through vm. After we apply the linear transformation T to each of the vectors in the basis B, we will get a vector in the vector space V, and each such vector can be uniquely expressed as a linear combination of the basis C. Pay attention to the scalars in this linear combination. They have two indices, and here is the pattern. The first index corresponds to the index of the basis vector in the basis C, while the second index corresponds to the index of the basis vector in the basis B. When you apply vector representation rho C, you simply take the scalars in each such presentation and write them as columns. Therefore, this is what you'll get as a matrix representation. Let's compute a couple of matrix representations, and first, let's start with a simple example of a linear transformation from column vectors of size 3 to the column vectors of size 4. Let's take a basis B of the domain C3, which consists of standard unit vectors, and basis C of the codomain C4, which also consists of standard unit vectors, but now standard unit vectors of size 4. Let's compute the matrix representation of this linear transformation S relative to the chosen bases B and C. This matrix is defined in terms of its columns, and to compute the columns, we apply the linear transformation S to each of the vectors in the basis B, and then we need to compute the corresponding vector representation relative to the basis C. We have a formula for S, so we can compute the values on the standard unit vectors. Also, C is a basis which consists of standard unit vectors, so it's easy to compute the corresponding vector representations. We have observed this in an earlier video on vector representations. But now notice that this matrix representation is this same matrix A that we would have obtained if we follow the procedure described at the very beginning of this video. These matrices turn out to be the same because we chose the bases B and C to consist of standard unit vectors. So this new definition of the matrix representation is a generalization of our previous understanding of what this matrix might be. And now, let's work out a new non-trivial example. We have this linear transformation T from the polynomials of degree at most 3 into 2 by 2 matrices. We are free to choose any basis to compute the matrix representation, so let's take nice basis. We will take a basis B of the polynomials, which consists of monomials, and we will take a basis C of the 2 by 2 matrices, which consists of these 4 simple matrices. The matrix representation of this linear transformation T relative to the chosen bases B and C is going to be a 4 by 4 matrix, and we will now compute this matrix column by column. The first column of this matrix is the value of row C applied to T of the first vector in the basis B. The first vector in the basis B is 1. It is a polynomial where the coefficient A is equal to 1 and the coefficients B, C, and D are equal to 0. We see a formula for T, so we know what T does to this polynomial. Next, we need to compute the vector representation row C of this matrix. For this, we need to decompose this matrix into a linear combination of the vectors in the basis C, which is easy to do because we chose a nice basis. Row C picks up the scalars in this linear combination and writes them as a column vector. So this is the first column in our matrix. For the second column, we repeat the same process, but now for the second vector in the basis B, which is polynomial x. This polynomial corresponds to the coefficient B being equal to 1 and coefficients A, C, and D being equal to 0. We can compute what T does to this polynomial, and then we need to compute the vector representation relative to the basis C. We decompose this matrix into this linear combination, which again is easy to do because we chose a nice basis C, and row C picks up the scalars in this linear combination and writes them as a column vector. This is the second column in our matrix. We do the same for the third vector in the basis B. It is a polynomial x squared, so we computed the value of the linear transformation. Then we decompose this matrix into the linear combination of the basis C. We write the scalars in this linear combination as a column vector, and this is the third column in our matrix. Finally, we take the fourth vector in the basis B, which is the polynomial x cubed. We compute the value of T. We decompose into the linear combination of the basis C. We read off the scalars and write them as a column vector. This is column number 4 in the matrix. So we have computed all 4 columns of this matrix, and now we can put them together to construct this 4 by 4 matrix representation of this linear transformation relative to the chosen bases B and C. Now, at this point, it's not yet clear how this matrix can be used. For example, in the case of the column vectors, the matrix representation had a very practical use. To compute the linear transformation was the same as to multiply the vectors by this matrix on the left. But this is not quite the case in general. We can't multiply a polynomial by this 4 by 4 matrix. So why would we even bother computing this kind of a matrix? I will answer these questions in the upcoming videos. If you found this video useful, please give it a like to help others discover this content, and subscribe to this channel to see more of these videos. In the next video in this series, we will discover properties of matrix representations. I will see you later.